Hello, IB Math SL2. You guys are looking at an example of a problem that hopefully looks familiar to you from what we did in class earlier. And you have three methods of actually working on this. You've got your zoom in method, and then you also have the table method, then you also have the algebraic method. You need to be familiar with all three of those, hint, 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 for maybe something like a performance task the next time that you have class. So here's your hint now. Try these out. I'm going to put this up here. And if your function is 4x squared minus 1 and your x value is 1, then you guys should be getting 8 as your answer. All right? So double check that you guys are getting 8 as your answer, and that would be a great way to prepare for next class. It's also up here because we are getting into more limit approaches. So we are going to be talking about how to find the instantaneous rate of change, all using limits. So remember, slope is the key, and limits is what we're using to figure it out. So from our class, we had some kind of function, and we actually were looking particularly at x squared. So I'm going to go ahead and say, let's say our function is x squared. And I'm going to go ahead and sketch it here. All right, there's our x squared. What we were talking about in class, though, is we want our slope at a particular point. And we're going to say that that point is right here. That point has an x value. It also has a y value. We're going to call this point A. And we're going to call this little a. And since a is going to be plugged into our function x squared, that means that our first point that we're going to be looking at, all right, is a and a squared. Then I'm going to choose a second point that I'm going to call b. I'm going to call this one b up here. And this also has an x value, and it also has a y value. So my second point that I wrote in black is going to be little b and b squared. Okay? What I'm going to say is, well, as b approaches a, so I'll use a color for that. As b gets closer to a, and I'll also write that, as b approaches or gets closer to a, then our x value, our little b, also gets closer to little a. And remember, a is the one that we actually wanted to find the slope at. So it's a good thing that our b is going to approach a, and our little b is going to approach little a, because a is actually what we want to find. We want to find what the limit is at a, or what the instantaneous slope rate of change is, at a. So what we're going to write up is just a general form of this. So in general, I'm going to put this in red because it's going to stand out. So in general, excuse me, try that again. Oh my goodness. Doesn't like the red one. Okay. So in general, it'll have to be in black. We're going to say that the limit as x approaches a, and the reason why we're saying x is because b is really representing any x value on the curve. We could have a b that's over here. Okay? We could have a b that's over here. It doesn't matter where your b is, but your b is going to be approaching a. It's going to be going toward a. So this one would be going toward a, this one would be going toward a. All right? So my limit as x approaches a, so whatever the x value is, we are now going to take our slope formula. So our slope formula is the f of x minus f of a divided by x minus a. So f of x is the y value of wherever the point is that you choose. For us, we're choosing b's. So f of x is the y value of wherever our b is along the curve, minus the y value at a. A is staying still. A is the one that we had in blue on our graph. So maybe I'll put that in blue for you guys in our equation. Okay, that's our blue guy. And then we have the x value again. Anywhere that that goes with our b, and then minus the a, which was also in blue in our picture. So that is still just the slope formula. Once you guys find that limit, it will give us whatever the limit is. I'm gonna do a little quotations down here. That limit will give you the instantaneous rate of change. And not only will it give it to you anywhere, but it'll give it to you specifically at whatever the a value is. So at a, since that's what we're really trying to find, okay? So algebraic meaning we're going to be doing the math here, okay? That's algebraic. Geometric approach is more looking at the picture and using the slope formula and that type of thing. Same thing. They're both going to go hand in hand here, okay? So our first example is we are going to use that same, we're going to use that same function that we had from before. I'm going to use f of x equals x squared. And this time I'm going to say that I want my instantaneous rate of change to be found at x equals 1. Okay. This is a little different than the algebraic way that we did earlier. And again, they're all limit approaches, but they're two different limit approaches. One of them is with the h in it that we already talked about. We're going to talk about again later today. But the other one is with this f of x and f of a. It's just a different way of writing kind of pretty much the same idea, okay? And you can do them both interchangeably. So we have this f of x at x equals 1. We are now going to let our limit, all right, as x approaches, what do we want our a value to be? I want it to be 1 in this case. Our f of x is x squared minus our f at 1. So if I take 1 and I plug it into x squared, I'm going to have 1. And then my x minus a, which is really x minus 1. Every time I write an equal sign, I make sure to put my limit down as x approaches 1. And if I factor x squared minus 1, I'm going to get x plus 1, x minus 1. Reason for doing this is I can go ahead and cancel out a common factor. So really what I'm looking at is finding the limit as x approaches 1 of x plus 1. At this point, I have simplified as far as I can, so I can go ahead and plug in 1. So I do not need to write limit again. I can go ahead and just plug in, and I should get 2. For the second example, I'd like you guys to try this method with the same, well, let's try a different one. Let's try, well, go ahead and try this one for now. F of x equals x squared again. This time, we're going to do when x is equal to 2. Okay? When you guys are working on this, you should wind up getting 4 as your answer. So the limit as x approaches 2. And then again, x squared is my function, my f of x, minus, if I take 2 and plug it in, I will have 4, divided by x minus, and then I have 2. Again, that is the slope formula. Don't forget that really all we're doing is the slope formula. Slope formula is all we're doing here. I would like you guys to go ahead and factor, make sure that you wind up getting 4. That is what you should end up with. Again, pause as you need to because you have this on video. So pause if you need to slow it down and try them. I just want to remind you guys of a couple limit rules because you haven't seen limits for a few months now. So limit rules, just basically quick rundown. If you guys have the limit as x approaches a, doesn't matter what the a is, if it's a constant, so remember a constant is any number. If I'm just taking the limit of a constant, so a straight horizontal line, it will always come out to be whatever that constant was because I have nothing to plug the a into. So if I'm talking about the limit of one number, it will be that number. That was rule number 1. Rule number 2, Remember, if you have the limit as x approaches a of a constant times a function, all right? Whatever that function is, if you have a constant in front of it that's multiplying by it, you can also take the constant out, and then you can just take the limit of your function itself. So if it makes it easier to factor out a constant, go ahead and do that. It'll make it a lot easier to work with sometimes. The third one is if you guys have the limit, again, as x approaches a, whatever a is, and you have two functions that are being added together. So let's say I've got f of x plus g of x. These could be something like a linear or a binomial, whatever they are. They're added together here. I can always separate them if that makes it easier. So I could also write them as the limit as x approaches a of f of x, plus I could also write the limit as x approaches a of g of x. And this is, if it makes your problem easier to work with, do it. If it doesn't make your problem easier to work with, then you can always leave it as is. And then for any continuous function, it's also true that if you had the product of f of x multiplied by g of x, you could also write it as the product of the limits. So we could say the product of the limit of f of x multiplied by the limit as x approaches a of g of x. Okay, this might not make your problem easier, but it might. So just know that these limit properties do exist, and you could use them if necessary. So this brings us to a very exciting point in our calculus career. What we've been talking about as the instantaneous rate of change is also known as the derivative. So we are entering a unit called differentiation. And differentiation is about how we take the derivative of a function at certain values of x. So the derivative at a given x value. Find the slope of the tangent at any point on a simple curve using the limit method. That's really what we're doing. You had any curve, and you were drawing the tangent, and then at any point, you were able to find the slope of that curve. So again, here comes the slope. So slope comes in, and that is the slope of the tangent line along the curve at some point. Derivative has a special notation. A derivative is written as f with a little parenthesis, with a little apostrophe, and then you put your x value, obviously, that's function notation, but with an apostrophe. Out loud, yes, this is how your book and also just IB in general likes to pronounce f, E-F-F, there you go. So f dashed, or f prime, or first derivative, they all mean the same thing as f with the little apostrophe. And then, of course, whatever the x value is that you plug into your function. So when you guys see that, what you guys are really doing is you are finding, so f prime is the first derivative, okay? It is also the instantaneous rate of change. Instantaneous, let's try that again. There we go. Rate of change. And then it is also the slope of the tangent line. So we have now one way to say derivative, two ways to say derivative, and over here, three ways to say derivative. Slope of the tangent line, f prime, f is the first derivative, right? The instantaneous rate of change. Those are three different ways of saying the exact same thing. Just find the slope of the tangent line at that point. And the way that we do it is with this limit approach. We're going to do a little bit more practicing with this limit approach.